at least the idea. Can you follow the lecture? No? No? No?
Question is that distribution data is coming 1 millisecond, whereas
Yes.
the profile update is going 100 milliseconds.
Yes.
That means when the distribution data comes, it won't update up to 100 milliseconds.
Yes, it is stopped when it is
Until this time slot comes.
Yeah, and then there are two environments.
Correct.
Yeah, they are not much correlated because the only correlation is that the vehicles is charged or not charged. Yeah. There is not a back, no. So there is no another effect of the results of the distribution network in the traffic. So this is just sending with this communication between the two software these stop and go signals when
100 milliseconds is a quite small. It's okay. The realistic time domain.
yeah.
It is a considerably quick response.
Yeah, exactly.
It can be considered.
Yeah, this is the assumption there.
Correct.
So, and then every time and then it goes.
So you mentioned somewhere it is a critical network. Critical network.
Critical network is the meaning. I don't know. Pardon me?
You mentioned somewhere it is a critical network. So how it is identified a critical network with the doubt.
Yeah, I don't know if it is a critical network. It's a distribution network in the one in the of the parking lot you mentioned. Yeah, it was the two feeders in the central part of the city, in which there was already some work for the optimization of the traffic. So we have collaborated with these people of the computer science department that they have done this study. So we have used also the results for the traffic into the city to implement this idea as much as possible, realistic, in order to show what can be done.
Sir, what if happens the charging stations which are isolated, standalone, self-sustained energy, maybe equipped with solar?
Yeah. So
Then
if
how we integrate with our traffic congestion in that case? If the parking lot is having some couple of charging stations,
yes, we have considered 10, so it is big. I mean, with 2, it is much limited the effect on the medium voltage network. If there is a solar panel there, it is a local production. So in the simulation, it is just a generator there that decreases the consumption. So it is a negative load, the solar panel. So that decreases just the consumption from the grid.
because when we considering the traffic congestion,
That is
the
true.
number of events which are moving,
Yeah.
while we model all that, some charging stations are self-sustained, and some are recurrent.
Yeah.
And how to integrate these both to consider and for evaluation in the grid power generation.
Yeah, this was not the idea to change the traffic flow or the use of the charging station, but just to limit, yes, to limit the maximum power, exploiting this capability that is in general provided by the manufacturer, at least of these fast charging, that the maximum power can be the rated one, but can also be decreased till very low. I mean, so the charging station of 50 kilowatt can also be lower, no? But at that point, you need to send the signal that is not by the user because the user wants to charge as fast as possible, but then needs to be a manager of the parking lot. So we have just considered that all the charging station, the maximum power was reduced. then there are all the fancy things to say, oh, we need to take into account the booking, I don't know, for some hours. So we know that one car is staying for a long time and so on. But this was just a decrease in the maximum power. Yeah.
Because more charging stations are electronic based, as
Yeah.
you mentioned.
Yeah.
So
This.
transients and switching losses,
Yeah.
suggest will be there.
Yeah. And these are not considered here because they are basically just a steady state condition.
And
Yeah.
the steady state condition.
Yeah, yeah. I mean, steady in the frame of the 1 millisecond. Good. The second part is the description of voltage control and coordination into the grid. And I'm taking the same tool of the last work that I presented, so the charging station. Here there is not the traffic simulator, but there is the communication network and the possibility to change the reactive power to some distributed generation. In particular, here we take into account that there are inverters of the solar units that can operate not only in the power factor 1, so with no reactive power injected or absorbed, but that they can also be controlled, so they can operate at a power factor that is lower than 1, so injecting or absorbing reactive power other than providing the active power of the solar. So how to use this? And before why, but it is quite clear, but how to use this, and we have tried to do this simulation, developed this approach. We can say at the beginning that there are 3 possible approaches to address the issues of coordinating the outputs of the various energy resources load with the action of available control means such as transformers equipped with on-load tap changer, or also capacitor static var compensator, if they are. And then there are local regulators. So you are in your PV unit, you measure the voltage at that bus and you control the reactive power of the unit on the base just on the voltage on that bus, so local coordination. And then there is, on the other part, the so-called active network management function of the central distribution management system. So a centralized optimization control that collects all the information from the networks, do the optimization as in the first part of this morning, and sends all the signal. There is also another idea that is the networked multi-agent system. So the controllers in each of the photovoltaic units, they make the decisions not completely autonomous, but exchanging some information, some coordinating information with the other controllers of the other photovoltaic units connected in the same feeders, and also the controller of the distribution, the transformers and so on. Some kind of distributed controller. In many cases they say, oh, the controllers are controllers with the communication network. So they are networked because they use the communication network, these messages that are sent not from the controller in the device, but from different controllers that are installed in the distribution network in different points. So the communication network and also the limitation of the communication network are important in this case, because if the communication network fails, probably also your networked control system will not reach the good results. So this is the motivation. Here there is just an example of a city, very small city near Bologna, and this is the distribution network with 15 kilovolt, and this is the change in very few years. In very few years, you see here, there is an image of the same network with many things in yellow, and these are active producers connected to the distribution network. So it means that they are photovoltaic, mainly photovoltaic installation into the network, and this change between these two figures, it happens in a very short time, in few years. No? In few years, there was a development of this installation. So there are 700 active clients. Active means that they are provided by some generating units with a power generation capability of 150 peak at the medium voltage, and you can understand that 150 megawatt peak for a network in which there are three transformers of 60 megawatt and so on. It is almost covering all the capability of the transformer in the substation. So the distributed voltage and reactive power VAR optimization, so I will call it VVO. The communication network used by these distribution system operators, in general, it is a shared communication network, so it is not based directly on all the fiber links that are instead used by the transmission operators. In general, for the distribution networks, the network used for the communication is less reliable or efficient than that, or private than that of the transmission network. So in general, it is the common communication for the cellular phones and so on. In order to limit, this may also include some cybersecurity aspects, but we don't cover that things. So in order to limit the required reinforcements of the communication infrastructure currently adopted, distributed and or multi-agent schemes, particularly those that do not assign special coordinated rules to specific agents, are expected to produce a more uniform traffic in the communication links than centralized approaches. So for the centralized approach, you need to concentrate all the communication in the central control and then spread the information all around. So there is a clear, heavy concentration of data in the data center. Here in the distributed, you have a more uniform use of the communication network. Moreover, this multi-agent system are expected to be less affected by limitation and constraints of some communication links due, for example, of high level of the background traffic. And we have already installed the co-simulation, and that was the same that we have used also for the other aspect. So what is the idea behind this study is to use controllers that have the capability to calculate, to measure, to estimate not only the magnitude of the voltage, so the RMS value, the root mean square value of the voltage at the bus, but also the angle. So they are equipped with a phasor measurement units, so PMU, measurement units function. So they have also this capability, other than also a memory buffer, so we can store the information in the previous. So assumption and reactive power compensators based on the electronic power converter, for example, the inverters of the PV station, capability to inject or a controllable value of reactive power between a minimum and a maximum. The compensators output are adjusted by a local controller agent connected to a node of the shared communication network. Is it reasonable? At this point, we have the procedure. cyclically, a couple of agents, so controllers in two photovoltaic units, are activated, or is activated, a couple, I do apologize, is activated and adjust the output of their respective compensators in order to produce a reactive power flow equals but in the opposite direction of the one flowing the distribution feeders. So with the idea is that you have, for example, this photovoltaic unit and this photovoltaic unit in this distribution network. This is the power network, with this is the transformer. And they, by using the information of the voltage, by using some information of the structure of the distribution network, they can evaluate what is the power, the reactive power that is flowing to the network from these 2 points, and try to create a reactive power flow in the other direction. So to compensate the reactive power exchange between the 2 points in order to reduce the reactive power flow into the network. The idea was this. And I repeated for all. I will try to be back now. And obviously, Q is not injected if the voltage is too high. So if in the bus the voltage is too high, you cannot inject reactive power, because in general we associate injection of reactive power with an increase of the voltage and absorption of reactive power with a decrease of the voltage. And Q is not subtracted, so it is not taken out from if the voltage is already too low. The minimization of the reactive power flows is expected to reduce the currents flowing into the overhead lines and cables, resulting in a reduction of losses. And we associate the reduction of the losses with also a reduction of the voltage drops, of the voltage deviation. Indeed, I mean, a reduction of the voltage means that the energy per charge, it is decreased. So we can associate the fact that there are less losses into the network with also that the voltage will be more uniform. This is the assumption behind this idea. So the more details of the scheme, I will try to use this the scheme here with this distribution network. You can see better there. You can associate always a kind of topology of the network with a Cron reduction of the network. So we can also represent this network with these here is visible. So you can take an equivalent of the feeder in radial condition with a network that just it is equivalent, but in which there are only a connection between one bus and the others. So it is something. So we can use this representation to estimate from the measurement of the PMUs, so the voltage phasors in H and in K, so in two different points of the distribution network, we can estimate the flow that is going directly from H to K in that moment. That is the flow into the network. So from this estimation, the two controllers, they can exchange the information to each other, because one needs to know the phasor of the other and vice versa in order to do the calculation of the flow. So these are the power flow calculation just for the reactive power between two nodes in which you know the parameters and you know the voltage both in magnitude but also in angle, in phase. So you see, recognize the cosine and sine. So both of the two, they are now aware of the flow of the reactive power between them, so they can implement a strategy that they inject a reactive power that tends to compensate this flow. Obviously, we don't inject if the voltage is too high, we don't subtract when the voltage is too low. In this way, they can compensate the flow. And so you see that one is taking a reactive power and the other is communicating to the other the value and take the compensating the other way. So if one injects, the other consume and vice versa. It is a reason. This is also in agreement, taking agreement with, and this is for two. And then it is repeated. So it is, in the literature, it's called the gossip-like controller, because there are many controllers and two at a time they are operating. So the first time was between these two and then between the other two and so on. So they go, and the procedures just keeps only two controllers operates in each instant, that here is of the order of seconds. No? So we are iterating in the time frame of seconds.
PMUs are time synchronized, GPS-based time synchronized.
Yes, the phasors measurement units, they need to have the synchronization in order to have the estimate of the angle, because they need this pulse that is given by also the GPS they give each second, so it is that synchronization in order to have a reference, because this is the reference for the shift of the waveform of the voltage with respect to zero time, and that gives the angle of the voltage. No? The angle is the angular delay between the peak of the voltage and the zero reference of the time. Is good? So there is also a coordination between this algorithm and the local controller. So we can say that this mechanism acts as a secondary voltage control, but the primary voltage control is there. I mean, there is the controller of the photovoltaic units that controls the voltage in the bus bar, taking into account the limitations. So these are the typical limitation of the maximum current in the converters and the maximum voltage in the DC bus inside the inverter. And in general, the local voltage regulator, at least in Italy there is a regulation, and it is of this type. No? So the regulator, the local regulator, does not do nothing if the voltage is near, this is the x-axis, the voltage is near to the rated value. So if it is between these 2 points, that is V plus and V minus, the local regulator does not anything. If the voltage is lower than V minus, it injects reactive power with some droop control. And if the voltage is above V plus in the bus, it absorbs reactive power with a droop control. So we have, we think that the secondary voltage control, this multi-agent system, can operate when the voltage is in in this range, because here it can improve the voltage after the primary control, no, the local control acts in order to compensate for the large voltage variation. So large voltage variation are for the local control, and the optimization of the voltage, it is for the secondary control. Is it fine? In general, the local control is faster than this mechanism because this requires some times to communicate and so on. It is also coordinated in this way also with the transformer, so the on-load tap change transformer. So we can see also the simulation platform that is very similar to the one that we have already represented for the mobility problem, no, the charging station. We have the EMTP, that is the electromagnetic transient program that does the time domain simulation into the network, and so the power system, the photovoltaic units, and so on. There is this communication model, and so they just communicate and between each other when I can also show to you perhaps a picture of what is the communication network. The power system is, you see, there are the units that are the controllers. Here there is an antenna because it is representing a cellular network, so in the communication, and there are the packets that are going around, and perhaps no, but it is not so important. I can show to you a movie, but probably also in the afternoon, that is just a representation, and you see the packet of information that are exchanged between the units, and also how these are elaborated inside the units within in the physical transport or logical blocks, and this is the connection with the MTP, so they gives the information inside the MTP. For example, the communication, it is in our case the phasor measurement, so they know the measurement of the phasor, the values of the voltage and the angle, and then the MTP calculates the calculation of the power flow, the reactive power, by using the previous equation, and injects or absorbs the variation of the reactive power. So hope that are there questions or something. So a first case, it is this network test case of IEEE with two antennas and the communication network, and these are the location in red of the photovoltaic units with these compensator, reactive power compensators, and in green just the areas of coverage area of the antennas. This is the meaning of these acronyms that are described in the communication network. And these are the details of the distribution feeder modes with the typical representation of the lines, and here below the transformer with on-load tap changers. We have considered 20 seconds of delay for each action of the transformer, and mechanical delay plus an increased delays. One of the aim also of this secondary voltage regulator is that to limit the voltage, the change in the tap of the transformer, because the more frequent is the change of the tap in the transformer, and it is the the less is the life of the transformer. So there is the maintenance. So we need to decrease the number of changes. And this is the representation of the injection or absorption of reactive power in the EMTP, just with this generator balanced. And this is the representation of unbalanced load that are a function also of the voltage. So there is a link between the power consumed by the load and the voltage. And so some results. So for this IEEE 37 system, you see OLTC with 8 tap, mechanical delay. This is the minimum variation. Time to the first change is 20 seconds. For the maximum delay of the regulators, these are, we consider 500 kVA PV units. This is photovoltaic units with an active power of 400 kilowatt in order to consider the limits. Agents that participate to the regulation cycle of the var volt optimization proceed, but it does not directly adjust the output of any compensator. This is the agent that is in the secondary side of the transformer, because the action of these controls needs to be coordinated with the action of the transformer. So if you like the idea, we can see the results. This is the start of the optimization. You see that the decrease of the power loss. So during this optimization, this exchange of things, the power loss decreases in time. So you see also the times in several seconds you decrease the losses. This is when VCC1 and VVC2 is blocks the variation of reactive power if the voltage is lower than 0.97 or higher than 1.03. So the V minus V plus that we considered before. So you see that the behavior is practically the same. VVC2 is less active because at the beginning there are several voltages that are outside this limit. So at the beginning it acts the primary control and also the transformer. So you see here the change that is due to the tap of the transformer that changes, and then this secondary voltage control acts after. And here it is not shown, but here you can also show dashed what is the situation with only the primary control, so without this secondary control, this multi-agent optimization. You see that the voltage is stable there, and that's all. No, the voltage, the power loss is stable there, and that's all. They increase the power losses because the voltage was too low at the beginning. So the voltage increases. Since the load are sensible with the voltage, the higher the voltage, the higher the consumption. So also the losses increase. So you see that the voltages are increasing and stabilizing in near to 1. You see here some of the points. These are the points, in some points of the network, and in particular 701, it is this point. So 1, it is the terminal of the transformer, and 1 is far. Oh, I don't know if this gives the idea. These are also the influence on the condition of the communication network. So you see that there are differences when you consider a background traffic higher and a higher also rate of interruption of some communication. So you see that if there is an ideal communication network, this acts, very fast. If there are problems, delays in the communication and also some packet that is lost, I mean some cycle does not complete, so we have not only one transformer tap change, but also the transformer acts also in other point. So for example here, and so. But much less than without this secondary voltage. This is the reactive power injection or changes in the controller. So you see that it's stable after a little bit 1 minute to 2 minutes, so it completes the cycle. The test case is also for 127 buses, the antenna, the transformer. Here we have 2 transformers with tap changes, the compensators of reactive power, the 5 units, and there is some logic here for the tap changers, and the results are here. The power loss that decreases in the same way as before. The voltage are increased and stabilized, and also there is we have also tried to see the effect of the variation of the photovoltaic, because if there is a cloud that is coming and just covering the panel very rapidly, what happens in our secondary? And so we have simulated this variation. You see time, so it is in the range of minutes. This is the change of the PV output due to the cross of a cloud in the sky. This is quite common situation. So we have represented this, and you see the behavior of the voltage control. So you see the power loss variation that is is affected by the transient, if it is taken into account the local control or not, but then there is the reduction, the usual reduction, and also the power loss here for this was for the small network and also the large network. There is a transit, but then it continues and it is stable. It is not affected by much. No, the result is different, but it is then it continues. Do you have any questions so far? So there are these simulation results, some details about the effect of the limitation in the communication network. So number of compensation cycles that are this exchange of information between the converters, incomplete compensation, the power loss decrease. You see that this is for several simulations, 30 simulations with the different random seeds. So you see here the mean value and the standard deviation, and you see that the results are quite consistent for all, with both for normal load level and also an increase of the load, so in different conditions. I don't know if we can see in brief the specifically developed ICT power co-simulation platform is used to test, to design also this multi-agent system. The strategy introduced the adopted gossip-like algorithm, is able to improve its robustness against the effect of non-negligible block error rate and delays in the cellular network. Specific aspects, the mechanism based on priority index implemented to allow the start of multiple concurrent compensation processes whenever a packet carrying critical information is lost or delayed. So if there is a packet that does not arrive, the procedure does not block, it is continuous. So, and then the coordination, there is the coordination with the local voltage regulator and the coordination with the voltage regulator of the on-load tap changer. And here there are details that we have already mentioned, and I think that for the moment we can finish here. because this is another topic, but probably we have a break. Or
multi-agent systems we are using, are they intelligent kind of thing? They are getting trained, learning from the real-time data.
it is not trained. So it is, I mean, the training, it is just, I mean, that we have designed the thing in order not to be blocked when there is no message that is going, reaching the results and so on. So there is a rule that says if the block is not receiving in some time, then you need to choose another compensator in order to continue the procedure, because if between two the communication is blocked, they are idle and they do nothing. So there is a procedure that says after a while of waiting the message, if you don't receive it, choose another one.
So it's a rule-based.
Yes, it is a rule-based, but it is not something that needs to be set up in order to adapt to the situation. We have changed the load, increasing, decrease, and so on, and the rules is always working as expected. So there is this, yeah. Good, so we can take, it is good to take the break? Good.
Yes, sir. Thank you, sir, for this
Do you
wonderful
have any questions? No. I'm trying now to also to see if I can show to you the